Okay, this is the last Laplace transform video. It's video number 5. We've already done a few examples of using Laplace transform to solve differential equations. Now we want to do a couple more examples using a situation where you have a differential equation, something like ay double prime plus by prime plus cy equals g of t, where g of t might contain, has a step function in it, an on-off function, u of t minus c, for example, where that's the function that's 0 until you get to c, whatever c happens to be. It could be 1, it could be 2, it could be 3.7, whatever it is, and then it jumps up to 1. It's 1 after that. And you can combine these step functions with other functions to create functions that you can create something that acts like a ramp. So it's off and then it suddenly turns on, for example, by combining a step function, by multiplying it by another function that's shifted and starts at 0. Okay, so in any case, so there's a couple. First, we have to, in order to be able to do anything like this, let's compute the Laplace transform of a function like u of t minus c. This function right here, the function that goes from 0 and jumps up to 1 at c. So c could be any number. C could be 5, c could be 7. I'm just going to do it generically with a c in it. Our formula should have a c in it. Remember the definition of Laplace transform is the integral from 0 to infinity, e to the negative st times whatever this function is, dt. Okay, so remember, u of tc is either 0 or 1. So what we do is we'll just split this integral up, split over those two possibilities. In other words, this will equal the integral of e to the negative st times 0 when it's 0, and plus the integral of e to the negative st times 1 when it's 1. Well, when is it 0? It's 0 from the left end of the interval up to c. So since we're starting at 0, it'll be from 0 up to c. And when is it at 1? It's at 1 from c to infinity, so this will be from c to infinity. You can always break up a definite integral. Right now it's going from 0 to infinity into two pieces. This one goes from 0 to c, and this one goes from c to infinity. Why would we want to break it up there? Because u takes on different values in those two places. Okay, so we just have to work out these two integrals. Well, it shouldn't be surprising what this one equals. Anything times 0 is 0. The integral of 0 is just 0. The area underneath the curve 0 is just 0. What about this integral? It's an easy one. It's just e to the negative st times 1. So that would be e to the negative st divided by negative s from c to infinity. Okay, remember, you can't really plug in infinity. You put an a there, and then you take a to infinity. You get the idea, though. If you're going to let t equal a, this is from t equals c to t equals a. If you're going to let t equal a in here and then let a get really large, that'll mean e to the negative st gets really small as long as s is positive. So this will be 0 as a goes to infinity, minus, if I plug in a c for t, e to the negative c times s over s. Over negative s, right? We have this negative in the bottom here. And of course the two negatives cancel, and I'm left with e to the negative cs over s. All right, so that means we can add this entry to our table. Right, we've completed another Laplace transform of a function. Let me see if I've still got the other one. Give me a second here. Okay, so I just inserted this Laplace table we've seen before. I can now add this next entry to the, I can add this entry to the bottom. Let's skip over these two here. Make a new entry. If our input function is u of t minus c, the Laplace transform of that function is what we just found out. It's e to the negative cs over s. And by the way, if c is 0, right, if c is 0, you get this function here, the function that jumps right at when t is 0, like this. Well, when t is, remember, we only really look at functions when t is greater than or equal to 0, so that's really the same as the function 1. So u of t is really the same as 1. So that would be just like this entry here, which is 1 over s, and that's what you'd get here, right? If c is 0, this equals e to the 0 over s, which is just 1 over s. It's the same as this entry here. So it should make sense. The only time it'll be different than that is when it jumps at some c besides 0. So for example, the function, this is the function u of t minus 2, and the Laplace transform of u of t minus 2 is just e to the negative 2s over s according to this formula here. Okay, so it's easy to take Laplace transforms of step functions. All right, so in fact, let's do a differential equation now. Let's do a differential equation. Now, there'll be one of these like this on your online Brightspace test. So here's an example. Solve y prime plus 6y equals 7 times u of t minus 8. I would say using Laplace transform, but the truth is you can't even do this one without a Laplace transform, so I don't even really need to say it. This is not one that you could do using the old method at all, because we've got this step function over here. What does this step function do? This is a step function that steps from 0 up to 7 at t equals 8. That's what this function does. So that's our right-hand side. This is the function, the forcing function. Notice this is only first order, so it should be a little easier than a second order. And I also have to give an initial condition. Let's say the initial condition is y of 0 equals 0. You can't solve differential equations using Laplace transform unless you have an initial condition. If it's second order, you'd need two initial conditions, one for y and one for y prime. But this one's only first order, so we only need this one initial condition to solve this differential equation using Laplace transforms. So remember the method. The method is always one. Take the Laplace transform of both sides to solve for Laplace transform of y after you plug in some of these, use these formulas basically and the properties of Laplace transforms. And then the last step, undo the Laplace transform of y to get y. So you know that as you do Laplace transform in reverse. All right, so let's do it. If you take the Laplace transform of y prime plus 6y, that'll equal the Laplace transform of 7u of t minus 8. All right, remember I can split these up, so this would be a Laplace transform of y prime plus 6l of y equals, here it'll be 7l of u of t minus 8. All right, so this first one, this is the Laplace transform of y prime. That's in our table, right? That should be right up here. Let me zoom in for you. That's this one right here. It'll be s times L of y without the derivative minus y of 0. So that's just this. This will be S L of y minus y of 0. We'll plug that in a second. This is still plus 6 L of y. That didn't go anywhere. Equals 7 times. We just worked this out. This is the one we just did. If you remember, it's e to the negative cs. Well, here C is 8. Right? This is C. So e to the negative 8s over s. That's what we found in our, that's what we just computed right here. When, for any c, in this case, c is 8. All right, so that's step 1. Now we have to solve for L of y. It shouldn't be too bad. Oh, by the way, I should substitute, right? Sorry for all the zooming. I should substitute my initial condition. Well, this initial condition is just 0, so this whole thing right here becomes 0. Could be different if it was a different value, a different example. So, all right, so I don't need to add that to the other side. I can just factor out an L of y here times s plus 6, right? Because I bring the 6 and the s are left over, equals 7 e to the negative 8s over s. And we're almost there. L of y is equal to 7 e to the negative 8s. Actually, let me write it a little differently. Sorry, let me leave that 7 on top. It'll be e to the negative 8s times 7 over s times s plus 6. Okay, so we're almost there. Now, first of all, imagine this e to the negative 8s was not here. Imagine it wasn't there. This would be real straightforward, right? You would just do partial fractions on this. You would do partial fractions on this, right? And then just invert it. You'd probably get 2 exponentials. Okay, well, that e to the negative 8s is there. So I need to show you how to do inverse Laplace transforms that have an e in front of them. Well, it turns out the first step will be, we still want to write this as e to the negative 8s times, in parentheses, we still want to do partial fractions. So whether you have that e in front or not, you still want to do partial fractions on this. So in other words, it'll be a over s plus b over s plus 6. Right? We're doing partial fractions just on the 7 over s times s plus 6, and this is the way it works. You want to write it as a fraction over s plus another fraction over s plus 6. We're doing fraction addition in reverse. We just need to find, a and b. Okay, so I think we've done this a few times now, right? You say, okay, well, 7 over s times s plus 6 equals a over s plus b over s plus 6, and clear fractions, so multiply both sides by s and s plus 6. And of course, they'll both cancel over here. So we get 7 equals, and we do this over here, we'll distribute this to both terms, and then in the first term, the s's cancel. In the second term, the s plus 6 is cancel. So I'm left with a times s plus 6, because that didn't cancel, plus b times s, because the s didn't cancel. And this has to be true for all s. So in other words, you can choose s's to plug in. If we plug in s equals 0, that'll be nice, because then this will be 0. This will be 0, and we get 7 equals a times 0 plus 6 equals b times 0. So that's not equal, sorry, plus b times 6. Sorry, b times 0. Okay, but b times 0 is just 0. So this is 0. So we get 7 equals, and 0 plus 6 is 6. So 7 equals 6a. And so it looks like we've got a. A is 7/6. Now we need to find b. How do we find b? Let's plug in something else. You could either, there's lots of ways to find it, but let's just plug in another value for us. If we plug in a value that we want to kill off a, I think negative 6 will work. Because if s is negative 6, if I let that be negative 6 and let that be negative 6, of course, it'll be a times 0, because negative 6 plus 6 is 0. So I'll get 7 equals a times 0 plus b times negative 6. So 7 equals negative 6b, and b would equal negative 7 over 6. Okay, so I've got it. Let's write those values up here. So Let me erase some of this. So it looks like now I can say this was 7, 6, right? And B was negative 7, 6. Okay, so I've got this. I've got the Laplace transform of y, right? That's what this is all equal to, right here. Just condensing it down. Now we've got the Laplace transform of y is equal to e to the negative 8s times 7/6 over s minus 7/6 over s plus 6. So y of t will equal the inverse Laplace transform of all that. E to the negative 8s, e to the negative 8s, 7/6 over s minus 7/6 over s plus 6. So we have to learn how to do this, and then we'll be done. I probably should have done this before we did this example, but so we'll come back to this in a second. Let's cover this now, and this is really the last technique that you need. So, this is the idea, is that, how about this? Let's, so again, this is sort of a side work or scratch work. We want to know, given some function f of t that we know that we already can find the Laplace transform of t, of f of t. So in other words, something that's in the table. You might wonder, what is the Laplace transform of u of t minus c times f of t minus c? Right? Well, remember, this is one of the functions we saw in the last video. Like for example, suppose this is the function. Suppose this function right here is the function f of t. Okay, then if this is f of t and say this is the number 3, then u of t minus 3 f of t minus 3 would be what function? That would be the same function shifted to the right 3. So 3 would go, so now this point here that started at 0 will now start here, and it'll look like this. It'll be the same shape, but it's just moved to the right 3, and then before that it's 0. Why is it 0 before that? Because of this is off or equal to 0 when, until t equals 3. So remember, we talked about this in the last video. This is a way to get a function f to turn on after a delay. The delay is 3 seconds because we put a 3 here and a 3 here. The t minus 3 causes this function to shift to the right 3. And the u of t minus 3 causes everything before it to equal 0. If we didn't have that, then it might just be some other thing, whatever f happened to do to the left of 3, but we don't want that. We want it to be 0 there. Okay, so let's try it. Well, by the definition, this is the integral from 0 to infinity of u of t minus c. You could think of c as being 3, for example. It's just a constant. In this problem, c is 3. T minus c dt. Oh, sorry, I forgot something, didn't I? I'm missing something from the definition. I wanted to also include an e to the negative st. That's part of the definition of Laplace transform. Okay, well here's the deal. Remember how this step function works. U. It's either 0 or it's 1. So the best way to handle an integral that has it in there, we just split it up into 2 pieces. It'll be an integral when u is 0, so it'll be e to the negative st times 0 f of t minus c dt, plus an integral when it's equal to 1. All right, well, when is it 0? It's 0 when t is less than c, and it's 1 when t is greater than or equal to c. So this, in other words, from 0 up to c, this is equal to 0. And then from c on to infinity, that u of t minus c function is equal to 1. So I just need to do these two integrals, and I'll have my answer. Well, as before, this entire function must equal 0 because we're multiplying by 0. So the integral of 0 is just 0. So that's 0 plus. Now we have to do this one. How about this? Let's do a u substitution. Let u, this is another integration technique. It's the easier one than integration by parts. Let's let u equal t minus c. You'll see why in a second. Then, by the way, you also find du equals dt here because the derivative of t is just 1. So du dt would be 1. Du is just equal to dt. You substitute in both of those into this integral, and we get the integral. By the way, so this is from t equals c to t equals infinity. Well, let's see, when t is c, what's u? U would be c minus c, so u would be 0 up to u equals infinity of e to the negative st. Of course, I don't need the 1 because they're just multiplying. And then it'll be f of, instead of t minus c, it'll be f of u. So I'm replacing t minus c with u. And then dt becomes du because of this. All right, so I'm almost there. Look at this. You recognize this? This is just equal to, this is equal to the Laplace transform of f. Hold on, there's actually one more thing I forgot to change, so I'm not quite ready to say that's equal Laplace transform of f. I forgot to change this t. This t also has to get changed. Whenever you do a u substitution, you have to change all the original variables to u's. So what do I do with that t? Well, I can rearrange this. Since it says u equals t minus c, I can solve for t by adding c to both sides, and I get t is u plus c. So I also have to change that one. So sorry, there's one more step here. We're almost done. Is the integral from u equals 0 to u equals infinity, e to the negative, I replace t with u plus c, in parentheses, f of u du. All right, so let me split this up. Remember, e to the negative u plus c is the same as e to the negative u. Sorry, I also forgot about the t there. There's a t there. Sorry, I'm sorry. I keep screwing that up. It's not t that's left over. It's the s that's left over. So this is the same as e to the negative u times s times e to the negative c times s. Okay, so all I did is distribute the s there and the negative, and then wrote it as two exponentials, right? If I multiply these two together, I would add their exponents, which is the same as just, this is negative us minus cs. It's the same as splitting it apart. All right, so I get the integral of e to the negative cs, I'll put this one first, and then e to the negative us from 0 to infinity of f of u du. Remember, our new variable is u. Well, since this first factor doesn't have any u's in it, I can pull it out. It's just a constant. E to the negative cs, integral from 0 to infinity, of e to the negative us, f of u du. Now, look at this right here. If we replace, you're allowed to use any letter you want for the integration. It's really just a dummy variable. It just exists there while you do the integration. The function e to the negative u times s is the same as the function if we replace u with t, which you can do. Just call it a different name. It's the same integral. We'd get e to the negative cs times the integral from 0 to infinity of e to the negative ts, f of t dt. And this is just exactly L of f. It's the definition of L of f, the Laplace transform of f. So, what did we conclude? Let me zoom out a little bit. We concluded that if you're taking the Laplace transform, if you want to take the Laplace transform of this right here, the answer is, we did all that work to get e to the negative cs times the Laplace transform of f. Okay. We could even add that to our table. Let me scroll over to the table. This will be in a table, any table that you get in the test. Of course, the fourth test in this class is open book anyway. But so if I wanted to do, if I had something more in this last one, if it wasn't just u of tc, but if it was u of t, sorry, of t minus c times f of t minus c, its Laplace transform would be e to the negative cs times Laplace transform of f, whatever f happened to be. If f was a sine function, you'd use the sine functions. F of, L of f of t. If the f here was a cosine, you'd use the cosine version. If the f here was like a t squared, one of these polynomials, you'd use that formula. Okay, so we'll just do a quick example of that. Suppose we have this function g of t is u of t minus 7 times, let's say, t minus 7 to the 4th power. See how that's basically this here? Where f here, f of t is t to the 4th, and we simply replace t with t minus 7 here. So the Laplace transform of that function, g of t, would equal e to the negative 7s times the Laplace transform of t to the 4th. Well, what's the Laplace transform of t to the 4th? That would be 4 factorial over s to the 5th from this row right here, t to the n. When, in this case, n is 4, so we'd get 4 factorial over s to the n plus 1, which is s to the 5th. So of course, 4 factorial is 24, so you'd get 24 e to the negative 7s over s to the 5th. That would be the Laplace transform of this function here. Well, okay, so it also means, by the way, that you can, let's look at that last center we just drew in the table. You can also use this table to go in reverse. If you ever have the Laplace transform of a function you already know times an exponential, that means when you undo it, it introduces this step function. So now we're ready to finish that problem that we were in the middle of. We slowly zoom back out to find that problem where it was over here. Yeah, sorry, it was, we were in the middle of it right here, right below it here. You scroll down, I forgot where I was on the page. Yeah, you see, this is where we were at the end. This is where we were at. We'll circle it in green. And I said, let's cover this now. Well, we just covered it. We were trying to do we started with this problem here. This was the problem. To solve this differential equation with this initial condition, the right-hand side happened to have a step function in it. So we did all this work here, split up the Laplace transform. We used our new tool. The Laplace transform of u of t minus 8 was this. We solved for L of y over here and got L of y times s plus 6 and divided that over to the other side. That's how we got this. And then we did partial fractions on that. And we're almost done with the problem. As long as we can undo this Laplace transform, we have to undo this. Well, didn't we just learn? If you want to undo a function that has this e to the negative 8s in it, what you do is you just undo this. In this case, they're separate, right? So I can split them. I'll undo this and this separately. and then multiply them both by u of t minus 8 and shift them over by 8. So let's do it. So what is the inverse Laplace transform of 7/6 over s? That should be an easy one. If you look in the table, you'll see that when f, I don't want to scroll back over there, I don't want to hurt your eyes. This is at the top of the table. When f is 1, its Laplace transform is 1 over s. And we can pull this 7/6 out, right? So this is 7/6, the inverse Laplace transform of 1 over s. And we just saw that that would be 1. So it would just be 7/6 times 1, or 7/6. But what we just said is that if I want to take the inverse Laplace transform of e to something, in this case we have e to the negative 8s times 7, sorry, that should say 8s, I'm going too fast, that should be negative 8s, 6, times 7/6 over s. Well, the only difference between it when it has that e to the negative 8s is it would be u of t minus 8 times this 7/6. Okay, so there's the first piece. We just undid the Laplace transform of the first of these two terms. Now I have to do the Laplace transform of e to the negative 8s times the second one. So now I have to do inverse Laplace transform of e to the negative 8s. What was that other piece? That other piece was negative 7/6 over s plus 6. Negative 7/6 over s plus 6. All right, so first, remember, what would be the inverse Laplace transform of just negative 7/6 over s plus 6? Well, remember, you can pull the constant out, and the inverse Laplace transform of 1 over s plus 6. What would that be? I don't know if you remember, but if you looked at the table, f and L of f, if you were to look up at that table again, one of the entries down there was e to the at, and it was 1 over s minus a. That's the one that looks like this. What would a have to be so that you get s plus 6 here, whereas this table says s minus a? You'd have to let a equal negative 6. Right? If a is negative 6, then you'd have 1 over s minus a negative 6, which is 1 over s plus 6, which is what we have here. So this inverse Laplace transform of this would just be the negative 7/6 times e to the negative 6t. That's the inverse Laplace transform of negative 7/6 over s plus 6. But we don't have that. We have an e to the negative 8s times that. So the inverse Laplace transform of e to the negative 8s times negative 7/6 over s plus 6 would be, it's the same answer here, except I put u of t minus 8 in front of it. And I also have to replace this t with t minus 8 to get it to shift over and start there. So times negative 7/6 e to the negative 6, and then in parentheses t minus 8. Okay, so overall we get y of t. It would be the inverse Laplace transform of the first part of the partial fractions plus the second part. So y of t, in fact, let me write this in black, it just shows up a little better, I think. So our final answer, the solution to that differential equation is y of t is this piece. By the way, why didn't we shift anything in this part? There's nothing to shift. There's no t here. So I didn't have to replace t with t minus 8 in the first piece, but it's u of t minus 8 times 7/6. And then we have this piece here. It looks a little weird to have the negative 7/6 in the middle. Let me bring that out to the end. Minus 7/6 u of t minus 8 times e to the negative 6 times t minus 8. That's it. You could make it look a little nicer. You could factor out. You could write 7/6 u of t minus 8, since that's in both terms, t minus 8 times 1 minus e to the negative 6 times t minus 8. That might be another way to write it. Just factored this out from both terms. That's also correct. They're the same. If you want to know what this graph looks like, it's off. See how it has a step function in it? It shouldn't be surprising our solution has a step function in it. It's off until t equals 8, which makes perfect sense since the forcing function didn't start until t is 8. So let's say this is 2, 4, 6, 8. So if I wanted to graph the solution, it would be 0 up until 8. And then what would happen? Then this function starts. Okay, so it's 1, but 1 minus this. Well, what's this when t is 8? Well, if I replace t with 8, I get e to the 0, so it's 1 minus 1. So it's actually here. And then as t increases, this gets small, which means the whole thing gets closer to 1. Okay, so it'll gradually approach 1 like that. As time goes on, this gets closer to 0, so the whole thing gets closer to 1. So that's the solution. It's a continuous solution. It has to be continuous, right? Because a spring mass system isn't going to just suddenly disappear and appear somewhere else. It's got an asymptote as it gets close to 1. So, all right, so there, that's it. How about we do one more, just so you can see it. This will be our last example. Sorry about that. Our last example. How about this one? Solve y double prime plus 9y equals 2 times u of t minus 4. So again, we have a step function in the right-hand side. And let's say the initial conditions are y of 0 is 0 and y prime of 0 is 0. Okay, so here's the solution. Of course, first you take L of both sides. All right, so this will be the Laplace transform of y double prime plus 9 L of y, just by splitting it up, equals 2 L of u of t minus 4. See if we remember this. Remember when we did this a second ago? This is e to the negative 4s over s times 2. That's the one we did earlier in this video. It's also in the table. All right, well, this is just plus 9 L of y. If you look up the table for L of y double prime, you'll get s squared L of y minus s y of 0 minus y prime of 0. That's what it'll be in the table. We developed that one a couple videos ago. Now, our initial conditions are both 0. So that means this is 0 and this is 0. That's kind of nice because then this whole thing simplifies to. I'll pull an L of y out and we'll have s squared plus 9 left over, right? S squared plus 9 equals 2e to the negative 4s over s. Okay, so we solve for L of y, and we get L of y is equal to 2e to the negative 4s. Actually, sorry, let me put that, leave that, I like to leave the 2 in the fraction. I'll pull the e to the negative 4s out, and then the fraction will be 2 over s times s squared plus 9, right? Because all I did is divide both sides by s squared plus 9. To kill it off here. Okay, so I've solved for L of y. That's the end of step 2. If you only got here and you couldn't get the rest, I'd give you a lot of partial credit. But the last step, undo it to get y. So I have to take the inverse Laplace transform of this left-hand side. E to the negative 4s 2 over s times s squared plus 9. So this is where we're going to have to use that new technique, right? I'll find the inverse Laplace transform of this, and then I'll shift it by, I'll multiply by, I'll shift it by 4 to the right, and multiply by u of t minus 4. So we have to do partial fractions on this fraction. It's probably the most annoying part of all these problems. Let's try to do it quickly. We've got 2 over s times s squared plus 9. That'll have to equal, by the way, you can't factor s squared plus 9, so it'll have to equal a over s plus something over s squared plus 9. Now, the thing you put up here has to be 1 degree less than the type of polynomial I have here. Since this is a second, we have to put this as a first order or first degree polynomial bs plus c instead of just a constant b. Okay, so since the denominator here is 1 power higher than this one, I had to use a higher order on top. But the procedure is the same. You clear fractions. So if you clear fractions, you get 2 on the left equals a times s squared plus 9, because the s's would have canceled. And then in the bs plus c, so there should be a plus there, I'm left with s. Right? We can use that same trick. Let's let s equal 0 and see what we get. If s equals 0, I get 2 equals a times 9 plus, this whole thing is 0, because if s is 0, then this is something times 0, which is just 0. So we can right away say a is 2 over 9. That's nice. I just have to get b and c. What would be another thing I could plug in? Let's plug in s equals 1 back into this expression. I'll get 2 equals a times 1 squared plus 9 plus b times 1 plus c times 1, right? Okay, so that means 2 would equal 10a plus b plus c. Okay, that's not too bad. It doesn't enable us to finish solving for b and c, although I could plug the a in, right? So I can say 2 is equal to 10 times 2/9 plus b plus c. And so I could, this is 20 over 9. I could subtract it on both sides. And I'll get b plus c equals 2 minus 20 over 9. Well, 2 is what, 18 over 9? So I get minus 2 over 9. So b plus c is minus 2 over 9. That's useful. If I can get either b or c, I could then go back and get the other one. What else could I plug in for s in this equation? Let's try s is negative 1. Seems like a perfectly convenient thing to plug in. Then I'll get 2 is equal to a times negative 1 squared plus 9 plus, in parentheses, b times negative 1 plus c all times negative 1. So let's work this out. We get 2 equals, well, negative 1 squared is still 1, and 1 plus 9 is still 10, so 10a. And it'll be, if I distribute this minus, I get negative 1 times b with negative times b times negative 1, so it becomes plus b, and then minus c. So now I can say, again, I could replace a with 2/9, and so I can say b minus c equals 2 minus 20 over 9, or negative 2/9. Look at that. If I add these two equations together, I get 2b equals negative 4/9, because the c's add up to 0. And it looks like b would be negative 2/9. And since b plus c is negative 2/9, then c would be 0. Okay, so, all right, so I got a, b, and c. I'm almost done. I finished my partial fractions. So let's go back. Let me zoom out now. That was kind of all scratch work. I was up here, and I found that a was 2/9, b was negative 2/9, and c was 0. Those are the three things I got in this decomposition. So now I can go back to here and say this is the same as the inverse Laplace transform of e to the negative 4s times, in parentheses, the first one would be a over s, so that was 2/9 over s, plus, and then it was negative 2/9 s, right, because it was bs plus c, We found that b was negative 2/9 and c was 0. So negative 2/9 s over s squared plus 9. So if I can undo this Laplace transform and undo this Laplace transform, then I could just use my shift with u of t minus 4, and I've got my answer. Okay, what is the inverse Laplace transform of 2/9 over s? I think we're all used to that now. That's just 2/9, because the Laplace transform of 1 is 1 over s. What's the inverse Laplace transform of this right here? This whole thing right here? Well, it'll be negative 2/9, and then how do you undo s over s squared plus 9 if you look in your table? I believe that's cosine. I always get confused whether it's cosine or sine, but if you look at the table, it's cosine. The cosine of bt is s over s squared plus b squared, so this would be cosine of 3t. Because the Laplace transform of cosine of 3t is, sorry, it's not quite, it'll be 3, right? If I did this cosine of 3t, it would be 3 over s squared plus 9, so I have to adjust for that 3. Right, I'm going to have to actually change my denominator to 27, right? Because if I took the Laplace transform of cosine of 3t, I'd get a 3 on top. That 3 will cancel with the 27 to make a 9. Okay, so I'm almost there. So the only thing I have to do is take this, multiply by, so y of t would be, it's that, but because of the e to the negative 4s, this is what we covered today, I have to put a u of t minus 4 there, and then times, now I have to shift all the t's to t minus 4. Well, there's no t in the first one, so it's just 2/9, minus 2 over 27 cosine of, instead of 3, it's 3 times t minus 4. Write that a little bigger. I replace t with t minus 4 because of the e to the minus 4s in front. It's a delay of 4 seconds, or 4 whatever units of time it is. So this is it. If I didn't have that e there, it would have just been these two things. But because of the e, I inserted this extra u of t minus 4, and I shifted my t to t minus 4, and that's it. And I used that last row of the table in reverse. Okay, let me zoom out one more time, find that table. I lost where it was on the page. It's way up here. Right, this last thing we put in the table, it says, if you're ever trying to undo a Laplace transform that has an e to the negative cs in front of it, you undo the regular Laplace transform back to f, replace t with t minus c, and put a u of t minus c in front of it. And in the last problem we just did, c was 8. Or sorry, c was 4. c was 4 in the one we just did. Right, so that's what we did. That's as hard as it gets. That's the hard one. So we can go over, if you're coming to class, you can go over this more in class, but those last two examples kind of illustrate the whole thing for us. This is the solution to that differential equation. We shifted it by 4 at the end. All right, so that's pretty much it. There'll be one problem like this in the last test, but like I said, even if you didn't get all the way there, they'll give you a lot of partial credit. As long as you can get up to the, you can just get up to here, you get a lot of partial credit. So, all right, that's pretty much it. And don't forget, the final exam will be Thursday, March 13th. I'll send out an email, but you should make sure you start studying for that as well.